All right. Howdy, everyone. Um, not really much updates to give. We're doing circular motion still. The joke of the day is why do they have to use the Apple operating system on the space station? Because they can't open Windows. It's neither of that's true. I don't know what operating system they use, but the joke is good. So just anywho. All right. So circular motion. This slide kind of has a nice little summary of everything we learned. So we found that you can find distance, the relationship between any angular, like a lot of angular variables, and then linear version is just multiplied by r. You want to go from angle to distance, multiply by r. You want to go from angular velocity to regular velocity, multiply by r. And then we talked about angular velocity is angle over time. Just like regular velocity is distance over time. And then the other thing I mentioned to y'all was this big old slide in the beginning, which basically said a lot of the equations I'm going to teach you are equations you've already seen. We just swap things. We just swap variables. All the kinematics equations, just replace them with rotational variables. Energy, just replace it with the rotational variables. Torque equals I, and so on and so forth. So we are going to see an equation today that doesn't fit that mold, but it does fit something you have learned. So we'll get to that when we get to that. All right, so this was kind of the last thing we chatted about, and this was kind of the newish thing. Well, yeah, new thing. If you're going in a circle, something keeps you going in that circle. There has to be an acceleration. There has to be a force keeping you in that circle. What keeps you on the earth? Gravity. Like, if there's no gravity, why would you stay on the earth? That is what's keeping you going in a circle on the earth. And we'll see some examples of other forces that keep you going in circles. But if there's a force, there's an acceleration. And due to some nice little math trick, that acceleration equals velocity squared over r. I didn't derive that. It's just one of those, just trust me. That the acceleration pointed inwards equals v squared over r. So great. And then we'll just go ahead and do a problem real quick. So at takeoff, a commercial jet has a speed of 60 meters per second, and its tires have a diameter of 0.85. How many revolutions per minute are the tires rotating? That's our first question. Now, I haven't mentioned revolutions per minute at all at this point, but it's something you've seen. It's on your car. It's exactly what it sounds like. It's how many revolutions it makes in 1 minute. So the answer here is going to be 1,350. In 1 minute, how many times does the tire spin? 1,350 times. That's what revolutions per minute means. Great, okay. How the heck do we get it? If we can find the angle per second, we can convert that. That's one way of doing it. That's kind of one of the easiest ways of doing it. So we'll go ahead and walk through that. For now, just trust me that we're going to be able to go from angular velocity, radians per second, to revolutions per minute. When we get to that point, I'll show you how to do it. And it's really simple. You only need to remember one thing. There's 2 pi radians in 1 revolution. So every time you go 2 pi radians, you make a full revolution. That's like the only thing you need to know to be able to make that conversion. So, anywho, what are we solving for? We're solving for RPMs. That's the short way of writing our revolutions per minute. And then for now, it's a trust me situation that to do so, we're going to find angular velocity. All right, our givens, we have velocity, good old regular velocity. And we have diameter. Now, pro tip, if anyone ever gives you diameter, you should immediately convert that to the radius. Like, we don't use diameter for anything. It's always radius. So we're going to take that and divide it by 2 because that's how you go from one to the other. 0.425. Great. All right, and that's kind of all we got so far. Now, see if you can figure out how are we going to get. So remember the first step, we're going to find angular velocity. See if y'all can figure out how we're going to do that, given what we have and what we need. I'll do. So we have regular velocity we have radius, and we want angular velocity. So anytime you have an angular version and you want the regular version, angular velocity to velocity, there's a really nice relationship between the angular version and the regular version. And this is one of those, it's just helpful to kind of have this in your head somewhere. Remember, the regular version is the angular version times r. That's the really easy way to, like, just really helpful to remember that. You want to go from angle to distance, multiply by r. You want to go from angular velocity to velocity, multiply by r. You want to go from angular acceleration to acceleration, multiply by r. It's a really nice, it's pretty easy to remember. If you just rearrange this, we're going to v equals, or omega equals v over r. Omega is angular velocity. So you just chuck the numbers in. 0.425, and that spits out the 141.2 radians per second. Great. Okay, that's not what we're actually solving for, but we're going to need it. So I want to go from radians per second to revolutions per minute. That's the goal. And this is just something, I mean, I think pretty much you all know this. There's 2 pi radians and 1 revolution. And if you're like, I don't know that, it's what's the angle in a full circle? It's 360 degrees. We don't use degrees. Go to radians. What's the angle of a full circle in radians? It's 2 pi. And now we're just going to do a unit conversion. So if we want to go to RPMs, we're just going to do a unit conversion. We're going to take this, radians per second, and we're going to use this little handy thing that I like that you all seem to have as a pretty down. So how many radians are there? We need to cancel out radians. We want to change it to revolutions. So revolutions over radians will do that for us. How many radians are there in a revolution? 2 pi. So you just chuck a 2 pi here. So we're just, great. That's going to get rid of our radians. That'll get us to revolutions per second. How do I go from seconds to minutes? We'll put seconds on top. We'll put minute on bottom. How many seconds are in 1 minute? There you go. And that's how we go from angular velocity to RPMs. The only thing that really, I mean, you need to know 60 seconds in a minute. But kind of only quote-unquote new thing is if you want to go from radians to revolutions, you just divide by 2 pi. Because there's 2 pi radians in 1 revolution. So every time I go 2 pi, I've made a revolution. You can basically think of I'm taking this number and I'm saying how many revolutions, just divide it by 2 pi. Every time it does 2 pi, that's 1 revolution. Another time. If here's a easy numbers. Say omega was 8 pi. I'm going to make the number really nice for y'all. So it was 8 pi radians per second. How many revolutions did I make in 1 second? How many 2 pi's fit in that? 4. This is the exact same thing as 4 revolutions per second. I went 2 pi. Then I went another 2 pi. Then I went another 2 pi. Then I went another 2. I went 8 pi. That's 4 circles. 8 pi is 4 circles. So it's a little easier with like nice round numbers like this. And that's all we're doing here. The number looks gross, but it's the same thing. So, you chuck all this in and you get an answer. You get that the revolutions per minute is the 1,350 RPM. Yay! All right, the rest of the problem is much easier. So if you're cool with this, the rest of the problem is even easier. Yeah, the new thing here was just, hey, can you go from linear to rotational? And then can you go from radians to revolutions? So kind of 2 skills, but neither skill is anything. We're not doing any crazy math. It's just multiplying and dividing things. Part B is really easy. What is the centripetal acceleration This is super, super easy because I've literally only given you one equation for centripetal acceleration. Centripetal acceleration is v squared over r. So just chuck in the numbers and you get the answer. I want centripetal acceleration. Oh man, what equations do I have that solve for centripetal acceleration? Oh, it's v squared over r. Like that is the equation for centripetal acceleration. It's the only one I've given you. So then you just chuck in the numbers. Velocity is 60, radius is 0.425, and that spits out the 8,470. I'll chuck it in my calculator to get the nice one. I think that one's maybe a little bit rounded, but it doesn't really matter. Yeah, it's basically that. All right, great. That's the acceleration keeping things. Everything on the outside of that wheel is accelerating that much to be able to stay on the wheel. Great. And then part C, I'm just going to tell you all what we need to find. It says, hey, I got a bacteria chilling on it. So there's a bacteria with this mass. What force must it cling to the thing? What force is required so it doesn't get flung off the tire? So I have the mass of the bacteria. It's some dinky number. 1 times 10 to the minus 25. It's a bacteria. It's really small. We're solving for force, and I have the utmost confidence you all can, again, really, see if you want to figure out, how do I figure this out? How do I find the force? This is called the centripetal force. It's the force, in this case, it's centripetal force because it's the only force acting on it. All right, any ideas? If you ever see force and mass, how do you think we're going to find force? F equals ma. If you know A and you know M, it's just chuck them in and there you go. Yay! So 1e to the minus 25 times 8,470, and you get a really small number. It doesn't need much force. Makes sense. No one's cleaning anything by spinning it super fast and flinging the bacteria off it. That's just not going to happen. They don't really need to hold on that much. Yeah. Yeah. Really, really, really small force to keep that bacteria on there because it doesn't have much mass. It's really, really tiny. Small things don't need much force to be able to hang on. That's why ants can climb walls and all that good stuff. They don't have much mass. They don't really have to have much force to hold on, climb ceilings, and all that nifty things. All right, yay! All right, so nothing too crazy here. Again, really the main things here: can you go from linear to rotational? And do you realize there's 2 pi radians in 1 revolution? That's kind of the only exciting things here. But it's a good exercise. All right, cool. Car goes in a clockwise circle as shown from above. There's my circle. It's going clockwise. There's my car. Sure, we'll do both of these. This one's probably unnecessary, but hopefully it'll be easy points. What's the direction of centripetal acceleration? We just calculated centripetal acceleration. Let's see if y'all remember the direction of it. Is the centripetal acceleration when it's on the right side? Up, down, left, or right? And I'll even draw little arrows. Up means up, down means down, left means left, right means right. Means exactly what you probably want it to be. No math here. So I'll give you like 20 seconds. Take your guess. 10 more seconds. If you haven't realized it, the key to this, it's in the name. All right, we'll close it out in 5, 4, 3, 2, 1. All right, so it's in the name. It's called centripetal acceleration, center acceleration. Which way does it point? Towards the center. It's in the name. And which way is my arrow? It's to the left. That's what keeps it going in the circle. Now, this next question is kind of I don't want to call it a review. This is the one where we start to get to the more interesting things. All right, same exact problem. Car goes in a circle, clockwise circle. Let's even chuck it on the right side. It really doesn't matter. What force actually keeps the car going in the circle? What force is responsible for the car staying in this circular path? So, is it the normal force, the gravitational force, the friction force, the tension force, or the spring force? What force causes that acceleration? That's the question. What force? We just said there's an acceleration. We were all cool with that. What force is causing that acceleration? Is the normal force causing that centripetal acceleration? Is the gravitational force causing that centripetal acceleration? Friction force causing it? Tension force, spring force? Which force is causing the centripetal acceleration? Where there's an acceleration, there is a force. My hint to you all is think about the direction of each of these forces. Whatever's causing the acceleration better point in the direction of that acceleration. All right, give you all like 10 more seconds. Again, we're looking at the car from above. You're looking down at the ground. All right, we'll close this one out in 5, 4, 3, 2, 1. All right, so what I'm trying to get us to, the reason for this question is we just said there's an acceleration pointed inwards. Like we just said that. Where we were, I think, cool with that. I don't actually remember. I didn't check the answers. I probably should have. We were cool with there's an acceleration towards the center. Maybe, maybe not. Hopefully. If we multiply that times mass, that gives us, and this is foreshadowing of the future, this is the centripetal force. M times A, we call that, if you multiply mass times that acceleration, you get the centripetal force. That force is not a physical force. That force is the sum of all forces pointed in or out. So, to kind of write this, mv squared over r, if we chuck that in here, is going to equal all the actual real forces. Centripetal force equals all the actual physical forces, like the ones we've learned about. Just like MA equaled the sum of all forces. Remember that before? F net equals MA. F net equals sum of the forces. You set them equal to each other. You do things. That's what we're doing here. MA, i.e. M times centripetal acceleration, equals all the actual forces. You have to decide what the actual forces are. So let's just go through our list. We got to figure out which forces are actually pointed inwards or outwards. We know there's a force inwards. Which one actually points that way? We just go through the laundry list. Normal force. Right now I'm standing on the ground. Which way does the normal force point? Up. It's the force of the surface on me. So great, I'm looking at my car. The ground's down here. Which way is the ground pushing the car? Like out of the page. Yeah. Out of the page. That doesn't point in the direction of the acceleration. So that's not it. Which way does gravitational force point? Into the page. That's not in the direction of the... So that's not it either. Friction force. So the easy one, this is one that's like a little trickier maybe to kind of think about. If there was ice, would this car keep going in a circle? If you all went over, you take a turn, you hit some water or some ice, your car doesn't have as much traction and it stops. The only reason your car can steer is because of friction. So friction is the actual force pointed inwards. And so in this problem, in this specific problem, friction is the only force, it ends up equaling this. So fun fact, you can find the force of friction by just how fast are you going around that circle in this case. So that's the answer. Now, notice I didn't look at the other two. Those ones are really obvious. Tension, there's no strings. Like, there's not even a tension force anywhere in this problem. Spring force, there's no springs. There's no spring force either. So yeah, let's see how we did here. Interesting, pretty good. And yeah, this is what I need to teach you. This is like the new thing. You all know F equals ma. Great. I'm just teaching you F equals ma for a circle. It just turns out in a circle, A equals V squared over R. Ta-da! If you're going in a circle, it's on this slide. There we go. It's the exact same thing, basically. So this is the F equals ma. And the new thing is that when you're going in a circle, A is V squared over R. And we look at, instead of up, down, left, right, we go in and out. Into the circle, out of the circle. That's our new kind of thing here. Instead of up, down, left, right, we got inwards and outwards. And if you add up all the forces pointed in and out, they equal mv squared over r. One little caveat here. If you're inwards, it's positive. If you're outwards, it's negative. So when we're doing this, and we'll do some examples right after this to kind of practice this idea. And this is a super handy thing. Like, it lets you calculate so many things. And the centripetal force always points towards the center. If it didn't point towards the center, there's no reason for you to stay in a circle anymore. But yeah, my hope with this one is that you realize it's just MA equals net forces. We're just not working in up, down, left, right. We're working in circle, out of circle. It's the same process that you've done before. And I guess A is V squared over R. That's also new. That's always going to be true. If you're going in a circle, this is true. And there's basically only two types of problems that there's like a roller coaster. I mean, there's more than this, but these are the two problems I've given you all. Roller coasters and a car going in a circle. There's other things that go in circles, but... All right. So let's practice building this equation. So here I have a roller coaster going in a loop. And it says at the top of the roller coaster loop, what equals the centripetal force? So, centripetal force, that's that mv squared over r. Remember, that equals the sum of forces pointed inwards and outwards. We only care about the ones that either point towards the center or away from the center. So this question is saying, at the top, what forces point inwards or outwards? If you're pointed inwards, it's a positive. If you're pointed outwards, it's negative. So, practice your free body diagram skills. What actual forces are acting on the ride, on the cart at the very top? And that's how we're going to solve this problem. And then you have to decide if it's inwards, it's positive. If it's outwards, it's negative. If there's more than one, combine them together. If there's only one, then you're done. So is it Fn plus Fg, Fg minus Fn minus Fg, Fn, or Fg? didn't draw it, please draw it. That's gonna make your that's what's gonna determine whether or not you get the answer right. All right, we'll do like 30 more seconds. Might be too much time. All right, like 10 more seconds. All right, we'll close this out in 5, 4, 3, 2, 1. Boop. All right, let's draw some forces. Gravity is the obvious one. We're on Earth. Which way does gravity always point? Down. Great. Easy peasy. All right. Any other forces? Normal force. There's a surface. There's an object on a surface. That means there's a normal force. Now, the question is, which way does that normal force point? So I purposely drew my box so that it was sitting down here. The normal force always points away from the surface. Like if I think I can reach it. If I stand on this chair, great. My hand pushes on the ceiling. Which way does the ceiling push on my hand? Down. Normal force is always away from the surface. When you're on the ground, normal force points up. When you lean on a wall, normal force points away from the wall. If you push on a ceiling, the ceiling is pushing back on my hand. That's a normal force. So, same thing here. Normal force is down. Fantastic. All right. Now we just do this part. Just add up your forces pointed inwards and outwards. Normal force, does it point inwards or outwards? Towards the center or away from the center? Towards the center, it's positive. Gravity, does it point towards the center or away from the center? Towards the center, it's positive. Boom, there you go. This is how you build. So like if you wanted to do this problem, i.e. it's the one we're going to do in like 3 slides. If you wanted to solve this problem, mv squared over r equals those two things added together. ma equals the sum of forces. The new thing here is that a is v squared over r, and we're worried about not up, down, not left, right, but inwards and outwards. All right, we had so much fun doing this one. What if you're on the bottom of the roller coaster? And I'm going to make this a little nicer. Here at the bottom, it's kind of a little gross. Pretend like it's flat. Pretend like this thing actually made a circle and not this weird, there's a name for the shape, I don't remember the name of it. Pretend like it's dead flat. Pretend like this thing's a perfect circle and the bottom's perfectly flat. At the bottom, add up the forces pointed inwards and outwards. Inwards is positive, outwards is negative. Draw your arrows. If you don't draw the arrows, you're making your life harder. Draw them, decide whether or not they point inwards and outwards, then add them together. And it's just like our normal stuff that you've done with forces, except instead of up, down, left, right, it's in and out. All right, we'll go like 20 more seconds. close this one out in 5, 4, 3, 2, 1. All right, we're going to do the exact same process. We got our easy peasy one. There's gravity. Gravity points down. Which way does the normal force point? Up, away from the surface. So then we just build our equation. So this equals mv squared over r equals normal force points inward, so it's positive. Gravity points outwards, so it's negative. And that's our answer. In and out. That's all we care about. If it's inward, it's positive. If it's outwards, it's negative. Now, something I want to point out here, just to connect this to reality. If we rearrange this equation and we solve for normal force, it doesn't ask us to here. I'm just proving a point. mv squared over r gets added to fg. Why is this interesting? When you all go to the bottom of a hill, say you drive down a hill and you get to the bottom, you feel yourself get pushed into the seat more, and the seat in turn has to push back on you more. Like when you all ride a roller coaster ride at the bottom of a loop, you feel yourself get pushed down a bunch, which means your seat's pushing back more on you to make that happen. If we look at this, and you can see that here, it's an addition. Gravity plus that, you get a bigger one. Where if we go to the one we just did, this one, if you solve for Fn here, Fn is mv squared over r minus fg. At the top of a loop, you don't feel yourself get pushed into the seat as much as you do at the bottom. Because math. And you can think of the concepts here. All right. So that's just to connect it to reality. I didn't ask anything about that, though. We will need to do this in a little bit. All right. What about on the right side of the loop? On the right side of the loop, which of the following equals the centripetal force? Draw your arrows. Decide whether they point inwards or outwards. Then combine as needed. It's very important you decide whether or not they point inwards or outwards. Inwards means towards the center. Outwards means away from the center. All right, we'll go 15 more seconds. All right, we'll close this one out in 5, 4, 3, 2, 1. All right. Which way does gravity point? Down. Great. Which way does normal force point? To the left. Great. Same exact thing. I'm just going to write this a million times. mv squared equals sum of forces pointed inwards and outwards. So this left side is just showing you that centripetal force equals that. I just keep repeating it so we get the idea. Normal force, inwards or outwards? Inwards, yay. Gravity, inwards, outwards, or something else? Gravity doesn't point inwards or outwards at all. Basically, gravity is not helping you stay in a circle. That's the whole point of this. Centripetal force is what keeps you going in a circle. Gravity ain't helping you stay in that circle. So, long story short, this is the answer. It's just normal force. You only care about the forces pointed inwards and outwards when we do this little equation. Everything else, you just pretend like it doesn't exist. Doesn't matter. It's the perpendicular part of it. We don't care about it. Just like when you're working with X, you don't care about Y. When you're working with Y, you don't care about X. When we're working on inwards and outwards, you don't care about the things that don't point inwards or outwards. All right. All right, let's actually do math with it now. So now it's this problem, but math. All right, you got a kid with mass of 40 kilograms. He's in a roller coaster. He's making a loop with radius of 7 meters. At the top, at point A, his speed is 10 meters per second. At the point B, his speed is 10.5. So that's point A, that's point B. The child's not holding on, doesn't wear a seatbelt. That doesn't, who cares? What's the force of, so let's just worry about part A. What's the force of the car seat on the child? That's what we're solving first. What is the force of the car seat on the child? And before we write any givens, I want to give you all a moment. What are we even solving for? What variable? Jot it down. See if you can figure it out. The force of the car seat on the child. That force has a specific name. See if you can figure it out. All right. Every single one of you is sitting, as far as I can tell. What do we call the force of the seat on you? There you go. That's what we're solving for. If you don't know what you're solving for, you're not going to get the answer. If you try to solve for centripetal force, that's not what it's asking for. It's saying what's the force of the seat on the child. That is the normal force. It's very important that you're able to identify what you're solving for. Otherwise, you're not going to get the answer. All right. Then we're going to write down the givens, and this is, easier. We got our mass, 40 kg. You've got your velocity at point A. That's 10 meters per second. You got your velocity at point B. That's 10.5. I'm just putting everything here. And you got the radius. Now, I keep using, I seem to be going back and forth. You can either make it a capital R or lowercase r. It doesn't matter. Pick your poison. If you notice I keep going back and forth, it doesn't really matter. So, both represent the same thing. They don't mean anything different. All right. How do we solve this? Well, I've got some masses and some velocities and a radius, and I want to relate those to forces. Anytime anything's going in a circle and you're talking, like forces comes up, you're going to do mv squared over r equals the sum of forces. Just like anytime any other problem, forces came up. How did you solve it? F equals ma. This is F equals ma. Ma equals the sum of forces. Ma equals the sum of forces. It just happens to be, we're just caring about the in and outs. And remember, A just happens to be v squared over r for circles. So, at the top, and we've already actually answered this problem. So, normally I'd give you all a chance, but we answered it, I think, like 2 minutes ago. What forces are acting on it on the top? Gravity and the normal force. That was the problem 3 problems ago. Do they point inwards or outwards? Gravity points in, it's positive. Normal force points in, it's positive. Ta-da, there's our equation. So, circular stuff's great. Like I don't even know how you'd solve this without this. Rearrange. So Fn equals mv squared over r minus m times g. I did 2 steps there. I subtracted fg over and I replaced it with m times g. mg. Just chuck numbers in and solve. This is why this stuff's useful. It lets you find forces that, gosh, again, I don't even know how you'd solve these otherwise. So I'm going to steal all of this. Put it right there. Steal my picture because I'm going to need that for the next one. All right. So, step 4 is always the easiest. Fn equals 40 times 10 squared divided by the radius, which is 7, minus 40 times 9.8. And we're not like skipping any. It doesn't even matter if there's friction. Like notice nowhere in the problem have I mentioned friction. If you want there to be friction, great. There's friction. Does it matter? No. It doesn't make it point inwards or outwards. We don't care about it. Friction doesn't affect this. Air resistance doesn't affect this. Like this calculation is pretty solid. Gets you pretty you can literally do this calculation assuming the only assumption we have to make here is that this thing's roughly circular. That's the only assumption that's required. Real roller coaster loops aren't quite. Yeah, the top is, so it's good enough. And we get our normal force of 179. Yeah, great. It's the one we got here. 0.43. All right. Part B. Part B, I'm going to show you all how to solve. And we're not actually going to bother with solving it. It's a little beyond what we need to do in this class. But I just want to show you all to show you this is a thing. At this point, we've only done like the top and the bottom. And the left and the right. But what if you're in between those locations? I just want to show you all this. I'm not going to ask a problem like this in the test, so don't stress it. But I do want to show you all that this is a thing. So I'm going to zoom in, because it's important to be able to see this. So at part B, it's over here. What forces are acting on it? The same ones we've been talking about. Gravity points down, and my normal force points inward. Great. Like, that's hopefully cool. Great with that. Normal force points inward. Easy peasy. Like, done. So if we start to build our equation. Part B is the exact same problem. There's just one little thing you got to be careful of. And again, I'm not going to test you all on this, so don't stress it too much. So part B, we're finding the normal force. We're going to do the exact same thing. mv squared over r equals the sum of forces pointed in and out. Great. So mv squared over r equals definitely normal force. Great. No problem. The thing that I would just want to point out here is Fg. It doesn't point inwards, but it also doesn't completely not point inwards. A part of Fg does point inwards. How do I show you that? I draw a beautiful triangle. So if I'm going to make normal force a bit bigger so that it doesn't get in my way. A part of Fg, if you make it into a triangle, you can see a part of Fg does point inwards. This part right here, let's call this Fg in, because it points inwards. So this is the whole, you remember like inclined plane? It's kind of the idea like a part of it does this. The other part we don't care about. Let's call this Fg perpendicular. We don't care about that one. Doesn't matter. But this part is just to show you that, like, when you're in between, gravity is helping keep you on the circle a little bit. Like, at this point, gravity is kind of somewhat helping you stay in that circular path. So, how would you find this FGN? So this is where you all got to remember this whole thing. Oh, I don't want that. You all got to remember if you have two lines and you make a straight line like this, that this angle equals this angle. So this 30 degrees is the exact same as that. So that right there is 30 degrees. Why is that useful? That means that FG inwards, this is just trig at this point, is FG times cosine of 30, because it's the adjacent side and the angle is 30 and hypotenuse is FG and trigonometry. Stuff that if I said this quickly at the beginning of the semester, no one would understand me. My hope is at least 50-60% of people understand what I just said. All right, great. So FG in, and just to kind of chuck this here, mv squared over r equals Fn plus mg cosine of 30. All right. Again, I'm not going to ask a problem like this, so if you're super confused, don't stress it too much. I just want you all to know components still matter, like they exist. All right, part C, also we're not going to solve. Part C is interesting. Probably wouldn't necessarily ask a problem like this, but it's not bad. I don't have any problems with it. Part C says, what minimum speed is required to keep the child in his seat at point A? And the way we're going to figure this out, like what the heck's going on here, let's go to the other extreme. Let's say this person goes faster. If you go really, 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 really fast, what's going to happen to my normal force? What's going to happen to the force of the seat pushing on you? Is it going to go up or down? Think of it, this person's like zooming. I mean, you can literally say it here. What happens as the velocity goes up? Does my normal force get bigger or smaller? Bigger, right? Like you go faster on a loop, you get pushed into your seat a bunch. Like if you ride the roller coaster, when you're going really fast, you get pushed into your seat a lot. So that's the extreme. If I go really fast, normal force goes up. But what if I get slower and slower and slower and slower and slower and slower? At some point, what's the normal force going to turn into? What's the smallest value the normal force can be? It's 0. Normal force is never going to pull you down. Like, that doesn't make sense. So, what's going on in part C? The minimum speed to make it up here is a speed such that the normal force is 0. Because at that point, the only thing keeping you in the circle is gravity. And if you're not going fast enough, you're just going to fall. So, part C, the key to this one, and I'll kind of just jot it here, is that the normal force is 0. Why is it 0? Because the extreme is that it gets really, really big. The minimum speed you need is such that the normal force is 0. If you're going slower than this, you're not going to make it around the loop. You'll get to the top and just, fall. So this is like the threshold. You go faster, normal force goes up. You go slower, you just don't make it. All right. This next one, we're also not going to solve in class, but I'll give you kind of the hints that you can refer to. It's the car going around a circle. Car goes around a circle. And it says if the coefficient of friction between the car and the road is 0.7, what's the maximum speed you can make this turn? This is the problem we started with. What keeps a car going in a circle? Friction. So the whole point of this problem is that mv squared over r equals the sum of forces pointed inwards or outwards. There is literally only one force pointed inwards or outwards, and it's the friction force. And that's, you do math and you solve it. And this is also really interesting because this is factual. If you all drive too fast, like if you all take a turn really tightly, your car will slip. Like if you drive too fast, friction won't be able to keep you on that circle. Yeah.
I thought the normal force on the right side is.
Ooh, that's a good point. So this is where you have to remember, we're like looking at it from above. It's like a new perspective. You're like looking down on it. So yeah, you're like up in the sky looking down on it. The normal force in this case is pointed outwards. If you're like, so like, imagine I'm looking down at this table. Yeah, the surface pushes away. Yeah, it's a good thing to remind us. Gravity still exists. Normal force still exists. I can't really draw this here. Well, I guess this is as good as time as any to tell you all this. Gravity, the way I'm going to draw gravity, you'll be like, what the heck? Gravity points inwards, and the normal force points outwards. And you're like, what the heck? What's this dot and this X? This is how I draw inwards and outwards. This is how we draw inwards and outwards in physics. It's really easy to remember, and I'm going to repeat it later on, so don't worry if you're like, oh my gosh, I didn't get this. So this is out of page, and this is into page. It's really hard to draw an arrow that's out of a page, so this is what we use. It's really easy to remember this using this one handy trick. Like a BuzzFeed article or something. But it works. It's really, really good. So these are arrows. They're vectors. Vectors are arrows. So think of literally an arrow you shoot from a bow, like a bow and arrow. If that arrow was going into the board, you'd see the back of the arrow. What's in the back of an arrow? The little feathers. You see the back of the arrow going into the board. You see the feathers on the back. You know what I'm saying? If the arrow's coming out of the board, what do you see? You see the tip of the arrow coming out of the board. That's how I remember it. So if you ever, this is going to be really important when y'all get to physics 2. You're going to have to know these. So foreshadowing. Yeah.
So is this like if you're in the car?
This is, you're looking at it from above. Yeah, so imagine the car's doing this, and I'm looking down at it.
And the other problem is
A roller coaster doing a loop. Yeah. In general, if there's something going in a circle, I very likely will give you all a picture of it because it's... I don't want you all to miss a problem because you don't understand the reference that you're looking at it with. And you're always going to be kind of looking at it dead on like this. Okay. Next slide is super simple. Just to see if we remember, how do you all go from angular velocity to regular velocity? This has nothing to do with this problem, but it's just to help us for the next slide. Times it by r. How do you go from theta to distance? Great. How do you go from angular acceleration to acceleration? Yay! Look, there's the next slide. How do you go from angular acceleration to acceleration multiplied by r? What is angular acceleration? It's whether your wheel is spinning faster or slower. Just like regular acceleration is whether you're getting faster or slower. Just add the word spinning in front of it. Whether you're spinning faster and faster and faster, or whether your wheel is spinning slower and slower and slower until it stops. Things that are spinning can spin, maybe they're not spinning, and then they do spin. They had to speed up. They had to accelerate. Same idea, same exact idea. Take everything you know from linear and just make it something spinning instead. The units are radians per second squared, just like acceleration is meters per second squared. We're not measuring distance over time, like how much that's changed. We're seeing how much my angle, to write this maybe a little differently, we're seeing how much my angle per second is changing, just like meters per second is changing. Change in angular velocity. Look, there's angular velocity. There's time. Great. So hopefully nothing here is too crazy. If you're cool with regular acceleration, you'll be cool with this. All right. So kind of the last thing I'm going to try to get through today is I'm going to try to teach you all how to find the directions of these things. I already mentioned it at some point. Now we're going to do it a bit more formally and just in practice. And then I'll show you all the angular kinematic equations. They're just like the normal kinematic equations with angles. And then next class, we'll practice those and we'll get into torque and we'll be fine. We're in a good spot. Okay, so I have a much nicer picture than the awful one I tried to draw before with my hand. So this is the right-hand rule. If you want to find the direction of angular velocity, you use this. You curl your fingers in the direction that you're rotating, and your thumb points in the direction of the angular velocity. So in this picture here, we're rotating about the z-axis. So you rotate your fingers, your thumb points up. That's the direction. What's the direction of angular velocity? In the positive z direction. Now, again, I want to remind you all it's called the right-hand rule. If you use your left hand and you do it, so great, right hand gets to the right things. If I do my left hand and I curl my fingers, I get the wrong answer. At some point, someone decided this is going to be right hands, and here we are. So you got to use the correct hand. If you really want to use your left hand, you can. Just know the answer is opposite to what you get. All right. This is only for angular velocity. This is only for angular velocity. This is only for angular velocity. This is not for angular acceleration. So then the immediate question is, how do you find angular acceleration? And to remind you all of that, let's just do an easy example. My velocity is to the right, and I'm speeding up. Which way will my acceleration be if I'm speeding up and I'm moving to the right? Which way should acceleration be? Should it be up, down, left, or right? To the right. So I'm going to kind of write this here. Speeding up. If I'm speeding up, my velocity is to the right. My acceleration is in, nope, that's wrong, in the same direction. If you're speeding up, your acceleration is in the same direction as your velocity. They help each other. It makes it bigger as time goes on. And you're like, why is he talking about velocity and acceleration? Same rules apply to this. We'll get to that. So, speeding up, velocity and acceleration, same direction. Let's do another random example. I'm slowing down. If my velocity is to the left, that's a negative velocity. What direction will my acceleration be to make this arrow smaller? Will it be helping it or hurting it if I'm slowing down? Hurting it. Same direction or opposite direction? Opposite direction. So a positive acceleration doesn't mean you're speeding up. That's the thing that people kind of fall in the bad habit of. You're slowing down if acceleration and velocity are opposites. You're speeding up if they're the same direction. The same applies to rotating stuff. If you're speeding up, your acceleration is the same direction as your angular velocity. If you're slowing down, it's the other way. So, to find the direction of angular acceleration, if you're speeding up, it's the same direction as omega, angular velocity. If you're slowing down, it's the opposite. So, long story short, you always got to find the direction of angular velocity. And if I'm asking for acceleration, you need to decide whether it's the same way or not. All right. How do I know whether or not any of that stuff I said just made sense? I ask you a bunch of questions about it. All right, so great. Here's an object. It's going clockwise. What's the direction of angular velocity? So try it out. I highly recommend, all right, before I even actually send this to you all, up is up, like on the paper. Down is down. Into the board is the X. Out of the board is the dot. Draw this on your paper / when I send it to your thing, do this thing and tell me which way your thumb points. Now, when I say out of the board, that could mean out of your paper. Replace the word board with paper if you draw it on your paper. Into the board is the exact same thing as into the paper. Draw this thing and up does not mean out of your paper. Up means the up, as I drew it. Up means up, down means down, into the paper means into the paper, out of the paper means out of the paper. Do the hand, match it, see which way your thumb points. When you draw it on your paper and you wrap your hand in the direction, your correct hand, your right hand, does your thumb point to the top of your paper, to the bottom of your paper? Does it point out of your paper, or does it point into your paper? And make sure you know what you're solving for. This is angular velocity, not angular acceleration. In fact, this is impossible to solve. I didn't give you enough to do angular acceleration. We don't know whether it's speeding up or slowing down. All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. Boop. All right. Great. I drew this on my paper. Yay. I take my hand. Oh no, my fingers aren't spinning the right way. What do? I turn them until they do spin the right way. Boop. Into the page. There you go. That's all you do. Make your fingers curl the right way. People that are online, this is going to be really jank to draw. I curled my fingers in that direction. So, there's my hand. You can tell because it doesn't look like a hand at all. I curled my fingers that way, and when you use your right hand, your thumb points out of the page. There's my thumb. It's pointing out of the page. Into the page. Sorry, into the page. Curl your fingers. Thumb points into the page. This thing's a pain in the butt to try to teach remotely. Great. Again, if you use the left hand, you get the complete wrong answer. All right. This problem is the exact same problem, so it's just nicer. So it's the same answer. A piece of gum stuck to a tire. It's spinning faster and faster. If the wheel is spinning clockwise, the piece of gum's on the right side. What's the direction of the angular velocity? It's the exact same problem with a paint job on it. Still into the page. It's the exact same problem. Look at the pictures. They're the same. And this one's asking for angular velocity. Great. Why'd I ask this? All right. A piece of gum is stuck to a tire that's spinning slower and slower. If the wheel is spinning clockwise and the piece of gum's on the right, what's the direction of the angular acceleration? If you haven't noticed, I'm solving for angular acceleration here. It's also very important that it's slowing down. You have to make two logical steps here. What's the direction of angular velocity? And is this helping or hurting it? That's the thought process. All right, I'll give you all like 20 more seconds. All right, we'll close this one out in 5, 4, 3, 2, 1. All right, so angular velocity, we already found points into the page. It's that x. Omega points into the page. Like, we're cool with that. Hopefully, it was the last problem. I'm not asking for angular velocity, but we need this. If this is pointed into the page and I'm slowing down, is my angular acceleration helping or hurting? Hurting. So which way? Same direction or opposite direction? There you go. It should be the opposite. It should be out of the page. Is it making it increase or decrease? There you go. Great. And that's how you do these. You just decide what's the direction of angular velocity. Angular acceleration, if you're speeding up, same direction. If you're slowing down, opposite direction. That's it. That's the strat. These are really easy problems to make up. These next two are kind of, I'm just going to give you all the answers so you can practice these on your own. This one's out of the page. This one I think is the exact same one, so I'll make it different. It's spinning counterclockwise. This is just extra practice in the future. Clockwise. Obviously, it's not spinning counterclockwise, so I'll just fix that super quick. Oop. Angular acceleration is going to be into the page. Yep, great. All right, those are just extra practice. Try them on your own. So fun. All right. Rotational kinematic equations are the exact same thing as regular kinematic equations, just everything swapped. And remember that when we measure angle, actually there's two things you all need to remember. Remember that theta is in radians, and remember there are 2 pi radians in 1 revolution. We already used that. We're going to use it again. So we do not work in degrees because degrees are made up. 360 degrees was a made up number that someone decided. 2 pi radians, that one is a set in stone. It's just how the world works. The ratio between the circumference and the radius is 2 pi. Why? Great question. Who knows? Pi shows up so many places in reality. 3.14159, yada, yada, yada. Interesting philosophical question. All right. Ta-da! Look, it's all the equations just swapped. Instead of V, you have a W. Instead of an A, you have an alpha. Instead of an X, you have a theta. They're the same equations. Also, you're spared. I'm never going to give you a problem with rotational where you have to split it into components. So these will all be like one-dimensional rotation problems. So, the one thing you might have to do, though, you might have some problems where I give you X and you need to convert to theta. Or I give you V and you need to convert to omega. Or A, how do you do it? You just multiply the angular ones by R to go back and forth. The other thing, never mix and match. Please never plug theta into one of the linear equations. Please never plug X into one of the rotational equations. Either you're working all in rotation or all in linear. And you can you can get X with theta, but just don't be plugging any radians into these. Make sure you convert from linear to translational, from translational to linear. You'll find in a lot of these problems, you can kind of work all in one and then convert at the end. You can do the whole problem linearly, and if you want the angular velocity at the end, just divide by R. Or you can do the entire problem in rotational, and if you want to get to linear, just multiply by R. Remember, that's the only difference. You want to go from one to the other. If you want to go from rotational to linear, just multiply by R. Like any variable. You want to go from theta to X, multiply by R. Alpha to A, multiply by R. Angular, great. Okay, I'm going to jump to a problem that's going to look gross, and that's only because it's a paragraph. It's going to be fine. So this is the one we'll start doing. We probably won't finish it today. You're like, oh my gosh, so many words. I just want to remind you all that anything complex is just a bunch of simple things. Just pretend like the rest of this doesn't exist. And ta-da, I made a problem that looked gross into a 2-sentence problem. One part at a time. All that happened here is I just showed you all 5 questions at once, so it looked intimidating. One part at a time. Pretend like the rest doesn't exist. During a very quick stop, a car decelerates at 7 meters per second squared. What is the angular acceleration of its 0.28 meter radius tire, assuming they don't slip? Try it. What am I solving for? What's given? Try it out. Don't worry about the rest of the problem. We're not there yet. All right, what are we even solving for? That's kind of the first thing. That's the new thing, how we do problems. What am I even solving for? What variable? Or what's the name of the variable? Angular acceleration. That's the funny A. Alpha. Great. What's given? Deceleration is given. Now, anytime I generally tell you all which way do y'all want this car to be moving? Left or right? Right. If I decelerate, is my acceleration positive or negative then? Negative. So we're going to make this negative. We're going to make that judgment call that we're going to say it's going to the right. Doesn't say, but we got to decide. And the radius is 0.28 meters. All right, I've got acceleration. I've got radius. I need angular acceleration. How do I go from angular to linear? You multiply it by r. Remember, if you all have the angular version and you want to go to the regular, just multiply by r. Now, in this case, we want to do the opposite, so just rearrange it. If you all want the angular acceleration, just divide the regular one by r. Do the opposite of multiply. So part A is super easy. Like, I want to go from linear to angular, divide by r. So -7 divided by 0.28. And we get our angular acceleration is -25 radians per second squared. To go from angular to linear, kinematics problems are very much, what am I solving for? What do I have? What equation relates those? They're very formulaic. If y'all remember back to doing your kinematics problems, it was just making a big old list of things. Great. On to part B. Cover up the rest so we're not scared. Pretend like it doesn't exist. Part B. How many revolutions do the tires make before coming to rest, given that their initial angular velocity is 95 radians per second? So this one, we do need to remember something. Something I put on the last slide, but it bears repeating. So there's part A. Part B, we are solving for the number of revolutions. Now, you may be like, that doesn't show up in any equation. Correct. But there's a really handy thing I told you all that we've used once already. What does 1 revolution equal? Yeah. 1 revolution equals 2 pi radians. What is radians a measure of? Is it distance? Is it velocity? Is it something else? What is degrees a measure of? Angle. Radians is just another way to measure angle. So, here's the thought process here, and this is kind of a new thing that you have to realize. If I can find the angle, if I can find how much angle I went through, I can find how many revolutions I went through. If I can find how many 2 pi's I did, how much my angle changed. Again, let's make up numbers. Let's pretend in this problem, that my change in angle was 8 pi. My angle changed by 8 pi. How many revolutions did I make? 4. 8 pi divided by 2 pi is 4. I went 2 pi, then I did it again. Then I did it again. Then I did it again. So I'll kind of chuck that over here as an example. If my change in angle is 8 pi, that equals 4 revolutions. Like they're the same thing. Leave that there as a nice little kind of like example touchstone. So, what am I actually solving for in this problem? I'm solving for my change in angle. If I find my change in angle, I divide by 2 pi. Yay, I have revolutions. Anytime you all have revolutions, you just need to kind of find, if it's revolutions per second, find angular velocity. If it's just revolutions, find angle. If it's revolutions per second squared, which would be nonsense, the angular acceleration. Okay. We do have a new given. It says my initial angular velocity is 95 radians per second. So my initial angular velocity is 95 radians per second. There's actually 2 more givens in this sentence that I'm going to give you all a second to see if you can figure out. How many revolutions do the tires make before coming to rest, given that their initial angular velocity is 95 radians per second? See if you all can find the other 2 givens that are in that sentence. All right, did you find them? There's a key phrase there that should stand out to you after doing so many physics problems. To rest. If something comes to rest, what does that tell us? What's like the thing that you know up to this point? Final velocity is 0. If my final velocity is 0, are my wheels still spinning? No. My angular final velocity is also 0. And if you really want to, remember, you just divide by r. 0 divided by anything is still 0. If you're not moving, your wheels aren't moving. So that's kind of the new. If you're at rest, your final velocity is 0 and your angular velocity is 0, which again makes your tires aren't spinning anymore. That's all angular velocity is how fast your tires spinning. Okay. The last, so great. We have everything we need to solve this problem. We are solving for the change in angle. That's our goal. If we find that, we divide by 2 pi and we're done. We have our initial angular velocity. We have our final angular velocity. We have our angular acceleration. So we have omega initial, omega final, alpha. Think of it this way. We have acceleration. We have initial velocity. We have final velocity. We're solving for delta x. It's that same idea. What equation here relates change in angle, initial final velocity, angular velocity, and angular acceleration? See if you can find it. There it is. Again, it's just classic kinematics. What do you have? What do you need? We have the final angular velocity, the initial angular velocity, the angular acceleration, and we can find the change in angle. Just, again, it's just like this one over here, y'all. You've done that. Final velocity, initial velocity, acceleration, change in x. Great. We're going to do it real quick. I know we only got 3 minutes, but we should be able to knock this out. So omega final squared equals omega initial squared plus 2 alpha change in theta. Then you just chuck your numbers in there. So 0 squared equals 95 squared. And now you can see why it's important we have this negative here. If you don't put the negative, it just doesn't work. Change in theta. So 95 squared divided by 50. So you get your change in angle is 180.5. I'll chuck it below that. So that's not what we're solving for. But we need this. This is a middle step. So that's how much my angle changed. Every time it makes 2 pi, it's 1 revolutions. So how many 2 pi's fit in there is going to be how many revolutions I made. Revolutions is my angle divided by 2 pi. Every time I do 2 pi, I make 1 circle. So how many times did that happen? I don't know. We got to plug in numbers and find out. Divided by. Now, be careful on your calculator. When you plug this in, if you don't put parentheses on the bottom, you're going to get the wrong answer. This is the classic mistake that people make on their calculator. If you plug this divided by 2 pi and you don't put parentheses, your calculator is going to think you're dividing by 2 and then multiplying by pi. You'll see what I mean if you make that mistake. It'll happen to you one day. Great. That's how many revolutions. That's how many 2 pi's I made. How many times my tire went in a circle. All right, we'll keep working on this one. I know this might seem like a lot, but really the only new skill here is to go from angular to linear, multiply by r, and 1 revolution is 2 pi. Now, we'll keep doing this, and at some point, if you're cool with kinematics, you'll be cool with this.